Okay, we're starting lesson 18, Algebra 1, Module 1. The title of the lesson is Equations Involving a Variable Expression in the Denominator. And this particular lesson comes on the heels of us looking at factors and how to solve equations with factors in lesson 17. And so it's connected. You'll see how that's connected here in a little bit. But this opening exercise, we're asking to consider when 0 is possibly in the denominator. So in this first part, you can see that it says no one says the check or wants us to check the answer to division problem by performing multiplication. For example, he says that 20 divided by 4 is 5. We know that's true. 5 times 4, the opposite of division, is 20. That makes sense. And so just using that as an example, let's take a look at A, B, C, and D. Why is there no real number that is the answer to the division problem 5 divided by 0? Well, the reason for that is, just as we said that 20 divided by 4 is equal to 5, and that means 5 times 4 is equal to 20. If we have the expression that we're considering, 5 divided by 0, what number times 0 equals 5? Well, there's no such number times 0 that equals 5 by the definition of multiplication of 0. And so this is why 0 can never be in the denominator. Look at the blue. That makes sense. Division and multiplication are inverse operations. Then look at the red. This is the reasoning behind 0 can never be in the denominator. So let's think, just like we did just a second ago. This also means that 0 times 17 equals 0. Is that possible? Yes. Yes. However, mathematicians are going to define any expression where 0 is in the denominator as undefined. Okay? No solution. Because we know that 0 divided by 0 is not 17. Expression or number C or letter C. Mavis says that the expression 5 over x plus 2 has a meaningful value for whatever value one chooses to assign to x. Do you agree? Let's take a look. Well, one of the things I notice is, what if I said x is equal to a negative 2? Because it says whatever value. Well, let's choose negative 2 and see what happens. So if we put in negative 2, that's not going to work. That gets us back up to problem A, where we know that A or 0 cannot be in the denominator. So this is not, we don't agree with C. D. This person says the expression 3x minus 6 always has the value 3 for whatever value one assigns to x. Do you agree? So again, we're looking at this problem and trying to answer the question whether we agree. This expression, 3x minus 6 over x minus 2, always has the value 3 for whatever value one assigns to x. Let's see. Well, I do notice something here. I notice that 3 can factor out. I noticed that because that's what we learned in the previous lesson, that I can actually factor out a 3, and then look what happens. That reduces, and you're left with 3. So I do agree with this. I do agree with this because no matter what you put in for x, regardless of what you put in for x, you're always going to get 3. There is one exception. And so I have to be careful. Whenever x is equal to 2. And so with this answer, we say, yes, I agree. However, x can never equal 2 because if it's 2, the denominator goes to 0. Okay, and so these are the kinds of things we're going to be looking at in this lesson. Positive video when you need to. So let's take a look at what you're going to be actually trying to do here. So in number 1, so as you look at this number 1 here, move forward here, hold on. It says rewrite 10 over x plus 5 as a compound statement. What they mean by that is, we're going to rewrite this 10 over x plus 5, and we know that x cannot equal what number? -5. And so that's what we're wanting to be able to do. When you're given an expression and it says write a compound statement, basically going back to our review from this, when we learned about compound statements, inequalities, it's the original statement, 10 over x plus 5, and x not equal to -5. Let's look at number 2. Number 2 says consider the expression and then answer the following questions. And there's, I believe, there are 3 questions, A, B, and C. So the first thing, is it permissible to let x equal to 5? So let's go over here and let's take a look. So if we put 5 in here, what happens? Well, 5 squared is 25, minus 25. 5 squared is 25, and so here 25 minus 9 is, anybody? Well, yep, that's 16. 16 times 9, that's a big number. So is it permissible? In other words, 0 over whatever 16 times 9 is. It doesn't even matter what 16 times 9 is. Can we put 5 in? Yes, we absolutely can. In fact, that's going to be 0 over 144. And so the answer to this is, yes, it's permissible. B, is it permissible to let x equal 3 in this expression? Well, take a look at this. We learned about factoring last chapter. We should remember that x squared minus 9 factors into, because it's one that we dealt with, x plus 3 and x minus 3. That comes directly from lesson 17 when we learned a little bit about factoring. And so as we look at this, the question is it permissible to let x equal 3? The answer, no. And the reason, if x is equal to 3, that factor goes to 0. And the whole denominator goes to 0. And so the answer to B is no. You cannot have 0 in the denominator. And then finally, C, give all the values of x that are not permissible. Well, all the values of x that are not permissible stem from that, this, and this. That would include -3, 3, and a -4. These values are not permissible because they make the denominator go to 0. Okay, we're going to wrap this up with 2 more examples. 2 more examples working together. And again, the skill is we're trying to identify when the denominator is going to go to 0. And whatever x value makes it go to 0, that cannot be a part of the solution. So here's example 1. Consider the equation 1 over x equal to 3 over x minus 1. A, rewrite the equation into a system of equations. In other words, a compound statement. Just like before, we're going to rewrite the original. Rewrite this. That's all we're doing. And then put the word and. X cannot equal 0, and x cannot equal one other number. What other number is that? It cannot equal 2. I'm getting this information here and there from this right here. Any value that makes the denominator go to 0, not a part of the solution. And then in B, solve the equation for x, excluding the values of x that lead to the denominator of 0. Okay? Okay, so now in B, solve the equation for x, excluding the values of x that lead to a denominator of 0. Okay, watch very carefully. We were asked to solve this equation. 1 over x is equal to 3 over x minus 2. We had similar problem with this earlier last week. We can solve this by thinking of this as a proportion. Some of you may have heard of the butterfly approach, maybe. I'm not sure if that's something you remember. 3 times x is equal to x minus 2. So 3 times x, cross multiply, because two equations equal each other, you can solve as a proportion. And then x minus 1 or x minus 2 times 1. Solve. And you get x is equal to a negative 1. So x is equal to negative 1, and x is not equal to 0, and x is not equal to, of course, the negative 2. These, because they make the denominator go to 0. Take a moment and look at that, rewind it, see what you got. The last one I'm going to do. Similar problem. Here we go. Rewrite the equation into a system of equations. So I'm going to rewrite it. X plus 3 over x minus 2 equal to 5. Just rewrite this. And x not equal to 2. That's it. That's it on that one. E, solve the equation for x, excluding the values of x that lead to a denominator of 0. Well, let's see what happens with this one. So I'm going to take this expression and solve. Cross multiply. Look what happens. X plus 3 times x minus 2 equal to 5 times x minus 2. Okay, so we've seen this before, haven't we? We've seen this problem before. So now let's move this over. X plus 3 factor out x minus 2. Going to have to save some room here, aren't I? What's left? Factor this out. We're factoring these things out. What's left is x plus 3, minus 5. Take this up here. X plus 2, or minus 2 rather, I'm sorry. And 3 minus 5. Oh, wait a minute, we got something here. Okay, so this can't be. So if you take a look at this, we came up with two factors. This is lesson 17 right here. But x cannot equal 2 because it makes the original go to the denominator of 0. So when I get to this point and I realize, wait a minute, that means I have the empty set. In other words, there's no solution. You can see how we're using lesson 17 in this one. And so this last problem is a great example as to how we're going to use all of our skills to solve equations and to also take out numbers that force the denominator to go to 0. Those are not possible to be a part of the solution set. So we're going to end the video like this and come back. We're going to actually do exercises 3 through 11 in class as practice. And we'll go from there. All right. See you guys. Talk to you in a little bit.